Great. So welcome to Machine Learning in the Physical World. So it's going to be taught by myself, Neil Lawrence, and Carl-Henrik Eck, who's sitting in at the front at the moment. And the idea is we're interested in what happens when machine learning technologies collide with the real world, physical world. So whether that's science or engineering, environmental sciences, and what we're going to do in this course is look at a set of approaches that we can use in those circumstances that are based on machine learning techniques. But they're also known in applied maths and statistics, where they're known as uncertainty quantification. Sorry, just put my cursor in the right place. Okay, so as a quick overview, I think I've got one of these lectures out of sequence in the slides, but they're correct on the main web page. I'll fix it on the slides. So I'm just going to give an introduction to set the context for what we're trying to do today. So it's going to be very nice, and you're all having to sort out your accommodation and everything else and stand on your feet. So it's not going to be too much technical today. And Carl-Henrik, in the next section, will start talking about some of the mathematical basis of what we're going to do. And then in week 2, we'll introduce more of that. Now, if any of you are doing Carl Rasmussen's course in engineering, hands up if you're doing that course. Yeah, it's quite complementary to that, actually, because we talk about these models in a different way. So there's some overlap, and I think it's very helpful when you are doing both. But if you're not doing both, don't worry. It's not a major issue. Once we've done that, the sort of Gaussian process models, which are sort of the main tool that we use for machine learning in the physical world, and talking about how we do inference in those models. Then we're going to start talking about, this is the slide where it's wrong. We're going to start talking about how we do decision making in combination with physical world models and machine learning models, and how we bring those two together, in particular sequential decision making. So I'll start introducing the notion of what we're going to rely on very heavily is the notion of a simulation. So in many fields, whether it's physics, supply chain, environmental sciences, the way that domain experts express their knowledge is with a computer simulation. And so a lot of this course is based on the idea that we have such a simulation, and that we're going to be working with such a simulation and interrogating such a simulation. So the question, though, is that you need to make decisions on the basis of that simulation. You may want to optimize it. You may want to do sensitivity analysis. And that's going to be the focus of some of these lectures here. But as I say, those slides have a slight errors on them, so ignore those two, but check the main notes. Well, that'll be the first 5 weeks where we talk about these techniques. And then what we're going to do for week 6, 7 and 8, what we will do is we'll do 3 special topics. Now, last year's special topics are on the online, so you can look at them, and they're listed here. And the idea is that you're going to look at these special topics and learn about simulations in the real world. So the first one is a simulation that Andre and Bryn and myself also worked on for giving government advice in the early COVID pandemic about, it's a simulation that's taken into account how the disease is spreading, and it was for the test, trace, isolate scheme. So that was the talk from last year. You can see that talk already. You can see the slides. There was another one that Scott Hoskins, who's a British Antarctic Survey, gave on climate modeling, and a third one that was on personalized medicine and simulation, or was it? Yeah, it was on more computational biology. But as I say, they're online, and you can see the type of domains that you can deploy these ideas in. And the reason we start doing that is you will do mini projects in mini groups, starting from, we're going to set that week 6. Yeah. When are we going to assign the groups, I guess?
So basically the idea is to start thinking about them week 6.
Yeah.
The sooner you kind of decide on what you want to work on, the more feedback we're going to be able to provide, right? But this domain there, those weeks are about figuring out what we want to do.
Yeah. So the idea is that you've learned the techniques in machine learning, and that you will, in your mini group, choose a simulation of interest to your mini group. So some of you may be on the AI for ER CDT, for example, and I think in your case that you group separately and look at something within that domain specifically. But others of you take inspiration from the simulations we've shown you. Or last year we even had one group that worked on what was Paddy's group they did again? They did some sort of bonding physics.
There was like lots of crazy, like we were worried that we didn't set the project very stringently, and then we got the result. We were super happy because there was no way we would have come up with all these cool
Just
things.
in terms of what the simulations people chose.
Exactly.
And the things that they chose to do with them to explore the simulation, so using the techniques. So what we're looking for is people to use a range of these techniques. And these lectures are to help with your inspiration in terms of what you'd like to do. Yeah. So just bear that in mind while we're going through the course, that you're going to be wanting at some point to come up with a simulation. Often, by the way, you don't necessarily want to come up with a, so in the real world, some of these simulations are very slow. So, you know, simulations for our weather take all morning to run on the UK's fastest supercomputer, right? And you can do analysis on simulations like that, but of course it's quite slow to do the type of processes we're talking about. So often people are trying to choose a simulation that's runnable on their computer that they can play with and explore to get to understand these techniques. And those mini projects are due in at the first day of next term. Yeah, so we totally spoil your Christmas, basically. That's our idea there. Okay. So on to sort of course material. Come in. So I like to go back to 1801 to start this type of thing. Well, to be fair, the New Year's Eve of 1800, I think it was, where a gentleman called Giuseppe Piazzi was sat in Palermo staring through a telescope, squinting, and he could see something a little bit faint like this. And over time, as he looked, it's super faint on that screen, what emerged was an object. And this object, what Piazzi was doing was he was creating a star map. So Piazzi had gone to Palermo as part of the formation of a new university, and he was at the forefront of this field that was astronomy. And what many astronomers were doing was buying very expensive equipment, often from London, as Piazzi did, and analyzing where all the stars are and building a catalogue of where all the stars were. That's the sort of thing scientists did in those days. And Piazzi was looking at this particular star that I've just shown, and he's also depicted in this portrait of him, and he logged its location. And as all good scientists do, he repeated his experiment the following night to ensure that he'd logged these locations correctly. But this star in particular moved. Which is surprising because stars aren't supposed to move relative to each other. And so he continued monitoring its location. Because what he discovered at the time, he wasn't sure, but what was announced some months later. On the 1st of January, 1801, or sometime in the night of, sort of that's the thrills people had on New Year's Eve, early in the morning on 1st of January, he found it. And this was reported in London some months later, that the discovery of what was a new planet, which is kind of pretty exciting. As it says here, so you have to know there's something called a long S, and you'll see that this has got lots of things that look like F's, they're long S's. So he concealed the discovery to preserve all the honor and observations to himself. So nothing different in the field of academia from then to now. Till after 6 weeks of close watching, he fell ill. It will not be in a situation with regards to the sun to be observed again until a month or two hence. So this planet that he discovered was lost, which was a bit sad. And it's an interesting problem because it's one of the first examples of an extrapolation problem, the prediction problem. That is going to involve understanding the physics of the solar system and extrapolating out to try and recover the planet. But what I sort of like about it is that this star itself everyone was excited about it because recently, before a new planet had been discovered some years before, Uranus. And Uranus was the first new planet to be discovered sort of since the times of the ancients. So Mercury, Venus, Earth, Mars, blank, Jupiter, Saturn. And what I'm showing you here is something known as the Titius-Bode law. And it's a law that gives us a functional relationship between the location in terms of distance from the sun in astronomical units of the planet and where we expect, and the index of the planet. So why this was exciting is someone had proposed this law and Uranus was discovered. It wasn't a very famous law, but Uranus was discovered at sort of exactly the sort of location that the law predicted. So that meant everyone was aware that there was a missing planet. And there was actually an international hunt to recover this missing planet. And Giuseppe Piazzi was unaware that he was involved in this international hunt because no one had told him yet, because it was 1801 and messages traveled slowly. But he was a member of this. They called it the Intergalactic or the Galactic Police Force or something like this. And it was led by a guy called Franz von Zach, who was a Hungarian astronomer working in Vienna. And Piazzi had discovered this planet, but then lost it again. So these are the readings as published, sort of, I think, but by the time they were published, it was sort of much later in the year. You can find, there's links online to the documents where they were published that he made of the location of the planet. And I've actually just plotted them. So there's some evenings when it's cloudy, so he can't see. And there's some evenings when it's there. And the question is, how do we predict where that planet is going to be when it emerges back? So by the time he's published this, he's kept it. Why has he kept it back? Because yes, it's clearly something. It could be a comet, it could be a planet. He doesn't know. He's actually using Kepler's laws, which say that it will be either parabolic or elliptical, according to whether it's a planet or a comet. So he doesn't actually really have enough information to be sure on that. And he hasn't predicted the orbit. So he's holding back. The theory is that he was probably holding back the data so that he could be the one to declare the orbit. But by the time he'd lost it, he hadn't worked out what the orbit was. So that led to this international research that you can find in the Google Books links, if you can read German, that was sort of conducted by this guy, Franz von Zach, that ran a journal at the time to try and recover it. And what I find interesting about this is, so Newton is after Kepler, and you only need Kepler's laws to do this. But, what's at the heart of what's going on here is the combination with observation of some data in the real world and some physical understanding of how you think the real world works, and trying to combine these data together to make a decision about where the planet's going to be. So that's very much the spirit of the time, this sort of reductionist period where everyone's finding that the world works according to physics, and Halley's Comet is no longer a mysterious object that's coming to us from the gods, but it's coming to us because we have some understanding and capability to predict when it will return due to laws of gravitation. Now, this is the hero of this particular story. Can anyone tell me who that is? No. He is one of the heroes. It's not Laplace. Yeah, good though. So was it? Gauss. Yeah. So Laplace is the other hero, and in fact, all of Gauss's work he credits as inspired by Laplace's work from before. But this is Gauss, who was 23 years old, I think, at the time, and Gauss managed to fit the orbit and recover the location of the planet. Now, in order for Gauss to do that, he didn't have computers. So he had to do, and actually there's Andrew Fitzgibbon, who is at Microsoft Research here locally, actually gives talks about how difficult this fit is. It's an extremely difficult optimization problem. Even today, if you were to use naive techniques and do these types of fits, because the correlation between parameters and the tightness of the fit means that you probably wouldn't be accurate enough to recover the planet. And Gauss in 1801, when he was 23, developed his own set of methods to do that fit. And those methods themselves, I mean, that's why we credit Gauss with least squares, and that's why we name the Gaussian distribution after, as we'll talk about in a minute. But interestingly, Laplace was actually really the inspiration behind why Gauss was working on this. But it took him 2 months to do the maths he needed to do to recover that. Now, in the modern world, you can do that very quickly on a computer. Most of the maths he needed to do was not the model, it was how do I fit these parameters, clever ideas for hand fitting the parameters. Whereas today, we can use numerical solutions. So this is the this is where I try and do my my very poor German. It's really nice here. And another thing, look, see that the use of the long S and the small s here, that's how you get the sharpest S in German. It's not beta, it's a long S. Anyone German here? It's sometimes even called SZ, isn't it? Yeah, so it's a sort of, that's a glyph combining those two things together. And the long S, as we know, at that time also existed in English. So horror of horrors, I'm going to do my German. Aus diesen Elementen hat Dr. Gauss folgende Urte der Ceres-Fernandii in vorausberechnet. Die Zeit ist mittlere für Mitternacht in Palermo. So what he's saying from this elements, I guess, stuff that's come before, Dr. Gauss is predicting the location of Ceres for these dates where the astronomical coordinates are given by Palermo, where he's actually discovered it. And here is the predictions. And Franz von Zach, who is writing this, so Gauss writes to von Zach collates this, it's an early journal, and then pushes this information back out with the predictions. And so von Zach himself was one of the people that then stared into the sky in a relevant position, but other people did and found the planets again in the place where Gauss had predicted. Interestingly, because it's just a sort of letter writing that he's reporting on, we don't have any of the maths that Gauss used to predict it. And that's why there's later a priority dispute between Gauss and Legendre around who invents least squares. But Gauss later claims, well, I did this using least squares. So it's a beautiful story. And one thing I really like about this story is that it's combining physical understanding with data. And this story itself is used as a foundational story of statistics, right? The field of statistics, because it's analysis of data. But you can see it's really physics. And what's happened since then is that these two worlds have split pretty much into statistical modeling, where we care a lot about data and we use simple models and randomized controlled trials and various other things, and mechanistic modeling, where as things have got more and more complicated, we tend to use numerical solutions to do things. And part of this course is really to bring those two worlds back together. But at the heart of that course, that challenge is something I'm going to talk about next. Oh, well, here's the publication. Clever to name your discovery after your funder. So King Ferdinand of the Two Sicilies was who gave the funding to Piazzi to buy his equipment. So he tried to name the planet on the new discovery of the new planet, Ceres Ferdinandii, or Ceres is the it's one of the Roman goddesses of agriculture, but she's associated with Sicily. And here's the publication. Very nice. And you're also thinking there's an odd little bit about this story because there is no planet known as Ceres. So what happened? Anyone tell me what happened?
It's in the belt.
It's in the belt, yeah. So Ceres is not considered. So actually in all that German, you'll see it's Hauptplanet or something is the term, main planet. And actually Ceres is now as Pluto. So it's not only 200 years ago where they did this, it was relegated to the belt. And it's the only dwarf planet in the inner solar system because it's circular. Oh, I can't remember what's the name of the one on the other side. It's in the Expanse all the time. You know, if anyone watched The Expanse, yeah, you see, you should know all this from The Expanse. What's the other one?
Ganymede? Wait, no, that's
no, Ganymede's around. Yeah, is one of the moons. It's the one they destroy in The Expanse, isn't it? Yeah. They found another big asteroid that isn't circular, so it's not counted as a dwarf planet, and that's made them realize, oh, there's a lot more going on out there. And actually, in that location between Mars and Jupiter is an asteroid belt, and that's where the whole of The Expanse is set. If you are interested in watching that. So it's a dwarf planet, and but it was only sort of relegated in about 1860. So for a while, it was considered a planet. And of course, none of us, I mean, Titian's Bode law is known as a law that isn't a law, right? Today, people, if you mention it, physicists get very upset. But I think it's interesting to me because it was taken quite seriously then. I mean, I guess the point is it was an observational law. I mean, planets do, I guess, sweep their orbits in some way, so they are separated in some form, but it's not based on that physics. So there it is as well. That's actually, I think that's a failure because they recently, was it New Horizons visited it? And it's got this, look, it's got a city on it. No, it doesn't. That would be cool. I think it's halides or something, highly reflective halides. So it does look like, and they've got quite close-up pictures of that. It's about, some people say it's about the size of Argentina. I like to think of it as about the size of Greenland because that gives you the sense of iciness. It's the sort of, because it's all covered in ice. Okay, so, but what does that mean in terms of the sort of modeling that we want to do today? So the key problem that I think that they faced that I want to sort of highlight to you, because thinking about this problem, going back to thinking about this problem is, I think, important in trying to understand what had to go through Gauss and more precisely Laplace's mind in when to fit. So they were fitting the orbit, which is a set of basis functions that take into account the Earth's movement and Ceres's movement. So it's some kind of sine cosine thing. But we can map the problem that they were solving down onto fitting a straight line. But the problem with fitting a straight line is there are only two unknowns. Yeah. And so you only need two observations in order to fit that line. Okay. So when we plotted the observations that Piazzi made, there were many more observations than the number of unknowns that are required to fit the orbit. So how do we deal with that? And of course, you know, you've done this all over your different courses, how you deal with that. But imagine that you're seeing this for the first time, because I don't think many of you will have been through the thought process of what that means. Because once you've got that third observation, this is the problem that Laplace thought about a lot. How do we deal with the fact that we now have three possible lines that can go through these observations? Because they're used to solving these systems. Of course, they're hard to solve because they don't have computers. But what we have here, or what they had here, was an overdetermined system. So we can sort of write that system down in this way. The challenge we get, you know, that you'll know from high school maths, is that once we have 2 points, we've got two simultaneous equations that we can solve for M and C. But when we add 3 points, we've now got three simultaneous equations. So we can get three different solutions, each associated with a line, according to which two of those equations we use. Because these data points are inconsistent with what we're seeing. The parameterization is inconsistent with what we're seeing in the real world. So this is the challenge of the overdetermined system. And this is where, I mean, going back before Laplace, before Gauss, this is what Laplace concerned himself with. So he's looking very fine there. I like the fact that he was very smart. He was apparently quite arrogant, but, you know, which, you know, a lot of scientists are, so I suppose we forgive him that. But he's looking very smart here, and he lived to quite an old age, which was impressive because he lived through all these different revolutions in France. And there's a great quote from Napoleon about him. Everyone knows the quote where he says, "Oh, I don't need this hypothesis," meaning when Napoleon asks whether there's God in these equations. But I think that's the more interesting quote, is that Laplace is at some point given responsibility for a civil servant job. And the quote from Napoleon about him is, apparently he was really bad at the job. And he was really bad because he totally micromanaged everything. And Napoleon has this quote that you can look up that is something about him managing the infinitesimal, because that was all stochastic calculus and everything else. So he was a very bad manager, but an amazing scientist. And we don't have, I can't tell you the name of great managers of the time, sadly. But he wrote this, and this is a quote that I think goes to the heart of what we're talking about here. And so now I get to butcher French. Who speaks French here, so I can butcher your language as well? We'll go around. So Laplace this is an essay on probabilities, which is about 14 years after Ceres is discovered, but he's in a retrospective moment here. So the quote I want to sort of have is, nous devons donc envisager l'état présent de l'univers comme le fait de son état antérieur et comme la cause de celui qui le suit. So this quote here, which we can do in French, or alternatively, we can just look at the English version. So this is the translation. We ought to regard the present state of the universe as the effect of its anterior state and the cause of the one which is to follow. Given one instant an intelligence which could comprehend all the forces by which nature is animated and the retrospective situations of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present to its eyes. Does anyone know what that, well, it says at the top, so it's two names. Yes, go ahead. Yeah.
What that means, or like what's the that?
Say again?
It was a question of the like, what's the that? Like, what's the thing?
Yeah, so yeah, what's
like a form of superdeterminism?
superdetermined? Yeah.
Essentially, even with like, even if as agents within our universe, we are unable to infer the core principles of the universe, there might be some agent outside of it that might have all the necessary parameters to predict the future.
Yeah, and so and this is, and he's famously associated with this quote, and it's called Laplace's demon and Laplace's Superman. He's not the first to come up with it. It goes before then, in the past. It's a little bit odd because the quote's taken from a philosophical essay on probabilities. One of the clues is the page number, page 3. It's quite a long essay. But it does closely relate to what's behind machine learning and the physical world, right? Just as you just said. If we have a model, so if we look at that quote, we can see in that quote, the present state is the cause of the next state. And if we have comprehend all the forces by which nature is animated and the respective situations of the beings who compose it. So that to me is model. Our model of the universe, physical laws, and situations being compose it. That is the data about what the current state of the universe is. And intelligence sufficiently vast to submit these data to analysis. That's our ability to compute. Yeah, so that, and when he says submit to analysis, he's thinking of what Gauss had to go through in terms of analyzing and making the prediction. But for us, we're just dumping that on GPUs nowadays. It can make the predictions, the future's no uncertainty in it. And that's very much, this is the heart of what I see as the core of machine learning. So this is not an equation really, but we combine a model and data about the state of the universe through computation to make predictions about the future state. Now, as we'll see in this course, we want to use those predictions for decisions as well. But actually, machine learning traditionally does not concern itself with decisions. It's something that operations research does and other fields. But if you wanted to do AI, I don't like the term AI, but I think a better term would be automated decision making. So decisions come in at some point, and we're going to start seeing that in a couple of weeks' time. But that to me is the formula underlying machine learning. It's also the formula underlying physics, because there the model is much more mechanistic, and the data is often sparser, right? So in physics or weather prediction, it's all the same situation. You're picking up we're trying to predict the future climate. So we're trying to take all the data we have from the past, and then we're running a very large scale model to predict the future. It also underpins statistics. The difference in why there are different fields obsessed with this is because they're interested in different parts. So like I say, in statistics and machine learning, we tend to focus more on data-driven models, whereas in physics and many of the physical sciences, they tend to focus much more on a model, even or supply chain, that is encoding your mechanistic understanding about how the world's working, right? Another thing that I would say there's a difference between, say, machine learning and statistics is in statistics, they often worry less about the quality of the prediction and more about the interpretability of the system to try and extract some information from the model. And it actually is really confusing because everyone cares about this same thing, but they care about different parts. So we make different decisions about how we approach the problems philosophically. And that's something you'll see when you do the most interesting thing, which is to work across the boundaries of the fields. But that, for me, is a very fundamental equation, and it's there in Laplace's book. And then look, we can still even do it. So this is, we have to, if you're in Cambridge, you have to talk about what people who were in Cambridge said a lot, because so Stephen Hawking has this quote that I dragged out, A Brief History of Time, which I think is pretty famous. People have even, I think it was Paul Davies wrote a book called The Mind of God on the back of this quote. If we do discover a theory of everything, it would be the ultimate triumph of human reasoning, for then we would truly know the mind of God. So Hawking here is saying that if we discovered the theory of everything, then we've got determinism, right? Now, remember, that was page 3 of Laplace's philosophical essay on probabilities. Page 3. You only have to read 2 pages more. Page 5. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. We know that 3 or more, blah, blah, blah. It's a less pithy quote, and I think I'm the only person I've ever seen giving it, and I've even decided to give it a name to counteract the dominance of Laplace's demon, because it's far more important, and it's what Laplace is saying. So I call it Laplace's gremlin. Of course, gremlins didn't exist in those days, but they're more recent phenomena. Maybe they don't exist now, but there's been films about them and things. Laplace's gremlin. The thing that interferes with the mechanism of what you're trying to do and destroys your ability to do this. And he says it's ignorance. We don't know any of that. And of course, in practice, we can't know any of that. So in some sense, it's a bit of a dumb statement. And that's why he made it. So he can destroy it 2 pages later. And oddly, everyone keeps quoting him on the straw man statement, which is very strange. So this course is going to be about the consequences of that, basically, I would say. There's 3 ways that this uncertainty can come in. Uncertainty in our model correctness, uncertainty that's arising from our lack of data about the state of the universe, and another uncertainty that we'll see is compute. We don't have the ability to do those computations, right? They end up, those climate models, every time they build a new supercomputer in the UK to do our weather, they go down to a finer sampling grid for their Navier-Stokes equations, right? Because the compute causes uncertainty as well. So that's what we're talking about, Laplace's gremlin. So where do gremlins come from? If you don't know what gremlins are, I mean, there was a film about them, but the original idea of the gremlin goes back to early air pilots, sort of in the days when people were first flying planes and they used to crash a lot. And of course, they crashed because of errors in maintenance and whatever else. But the sort of a myth grew up around the creature known as the gremlin that interfered with things on the plane and broke parts of the plane, causing it to crash. And it was a really big feature of early pilots, particularly in wartime, to think of these crashes as being caused by this entity, the gremlin. And there's stories of people seeing one on the wing just before the engine failed. And I think it's quite a nice way of embodying this notion of uncertainty. And actually, so you can see that they were using, this is a wartime poster in Britain, where they're trying to warn people to stay tidy, and keep things in order, because of course, disorder is how gremlins breed. So Laplace's gremlin. How does that relate to our linear system? Well, Laplace knows about uncertainty. So what does he do? He adds a new parameter to that system. The earlier system had 2 parameters, m and c. And here, Laplace is going to add a new parameter. And it's a special parameter because unlike m and c, it's more like y and x in terms of it has its own index. And somehow I updated that just before and seem to have broken that. What this is supposed to be saying here is if we get that first point now, so if we substitute into the equation above, it's now 3 is equal to m plus c plus epsilon 1, that should say, where the underscore 1 is there. Okay, plus epsilon 1, meaning that every time we observe a point, that point is itself corrupted by noise. And the noise is different at each time. So I'm going to start using that term now, noise. Epsilon 2. That term doesn't come until, I believe that term's coming from sort of radar operator characteristic curves, so ROC curves. So again, Second World War. I think at the time they would have talked about it as error. And now I can, if I associate with each of these equations a separate parameter, epsilon1, epsilon2, epsilon3, that should read as, my LaTeX hasn't passed for some reason. Now I've converted this underdetermined system into what? What's this system now? It's now got 1, 2, 3, 4, 5 parameters and 3 observations. So I've converted the overdetermined system into what? Yeah, underdetermined system, yeah. So I've actually switched. I've taken this overdetermined system and it's now underdetermined because I've got 3 new parameters that should be clear in the slide, but aren't: epsilon1, epsilon2, epsilon3. Yeah. And what did Laplace say the solution was for dealing with our ignorance about the error? So what Laplace is saying is, in any of these observations, you've got your world model, and then there's something that you're not accounting for in your world model, and we're representing that as epsilon1, epsilon2, epsilon3. How do we deal with that? What did Laplace tell us? And the quote. What's the essay on? Probabilities. Yeah. Normal distribution. So actually, there's a really interesting story behind this. Laplace did this way before Gauss, but then he got really into what should this distribution be. And he, I always forget the name of his principle. His Laplace's principle of least, of least something. If you search that bit up, Google will fill in the last word. So that's why you don't have to remember these things anymore. Least indirection or something like that. And it's the sort of principle that you should introduce as little information as possible into the system when defining these probabilities. And he did an enormous amount of work to try and define, what was it? We're going to get to that in a minute. At the moment, at that time, they didn't have that concept, but we're going to bring that in a moment. Yeah.
Principle of indifference.
Indifference, yes. Principle of indifference, yes. Thank you. So Laplace's principle of indifference is that we should not introduce any information if we can avoid it. And then he spent a lot of time trying to work out. So what I'm showing here is effectively the way we would represent this in a regression problem today. But what it's saying is that y given x is governed by a function. In this case, this function here is our y equals mx plus c. So we could substitute mx plus c in here. But we're saying that's the probability distribution where the mean of this function is given by that linear regression. Yeah. And so that's effectively saying that epsilon is sampled according to a Gaussian density. So he's saying that epsilon is drawn from a Gaussian. Now, why did Laplace did not come up with this for this purpose? Laplace did invent the Gaussian density, but for some other purpose. And Gauss even credits Laplace for it. Also, it was invented independently by de Moivre. But Laplace did invent the Gaussian density for doing Laplace approximations. And Gauss mentions it. And Gauss says, well, I'm going to use this as the error function. They would have called it the error function at the time. But Laplace spent a lot of time trying to derive error functions that minimized the number of assumptions he could include. And they turned out to be very complex probability densities and very, very difficult to do the maths of fitting. The reason why this becomes very popular to do the maths of fitting is if you make this assumption, then optimizing that system turns into least squares, which is kind of the way we're all now taught at high school to do it. But we're never taught this process about why you, well, you may have been, but I never was, about why you end up at least squares. So you're making an assumption about this piece of the world that your model is missing. So you have your sort of model of the physics, and then you have your model of, and there's other crap happening that does something. And that's where the principle of indifference comes in trying to sort of describe that. But as someone said now, so that's actually leads to a stochastic process. And we're going to look at processes for doing this. So functions that actually are a bit more complicated than this, but based on the Gaussian itself, that allow us to fit functions with a lot of uncertainty in a very flexible way. That's going to be at the heart of a lot of what we do, and that's going to be the Gaussian process. But before we just talk about that, I want to sort of talk about Daniel Bernoulli. And I mean, this is very, so Bernoulli predates Laplace, and I think the Bernoullis, a lot of what Bernoulli said, Bernoulli and his brothers and father inspired what Laplace thinks. He's, in many respects, he's summarizing what Bernoulli said. But what's interesting going back to Bernoulli, remember Laplace said the curve of a simple molecule of air. Well, this is, I think, the first sort of serious work that stands the test of time on what happens in gases and liquids. So Daniel Bernoulli is writing about this in, I guess, the 18th century. And what's interesting about that work is he's very early on in introducing the notion of the conservation of energy to look at what is something like a Navier-Stokes equation. Very sad thing about that work, I can't remember if his father was Jakob or Johann, because there's so many Bernoullis. I think it's Jakob. His dad didn't think he was a great mathematician, read the work, stole it, and published it under his own name. How nasty can academics be? The brother was thought to be the better mathematician, and basically, and it kind of destroyed, as you can imagine. Imagine if your dad did that to you. But it's now kind of very clearly known that he talks about fluid flow and the physics of fluid flow. So it's one of the earliest pieces. Actually, now we do end up, now you're all in Cambridge, you do end up sometimes having to read bloody Latin for the what's that called? What do you say at the beginning of dinner? I can't remember anything today. Oh, grace, you say, you do the prayer at the beginning of dinner. So yeah, I was doing it on Wednesday. Someone suddenly hands me this paddle and you've got to do Latin. So here's, of course, they wrote all their science in Latin in those days, although Bernoulli was Swiss originally, but working in St. Petersburg at the time. But what he was talking about is systems like this. I've got a slight bug in my code. So the curve of a simple molecule of air, and what I'm going to do is start all these molecules going in the same direction. There's a slight bug in my code where molecules jump on top of each other there. Apologies for that, but they will eventually separate. What's interesting about this is we start all those balls going in the same direction, and we can think about maybe if Bernoulli's trying to do something Newtonian in that space, that's what he might think of in the model of how a gas works. But when we can simulate, what we see is very quickly they're not going in the same direction. And the reason is because they look like they're going in the same direction, but I put very small differences on their sort of x velocity. I sampled their x velocity from some direction. And as these balls start to collide into each other, they start to go off in random directions. Indeed, it's a chaotic system. So I was reading something from Feynman recently that I can't reconstruct exactly, but it was basically saying, the probability of you putting a ball down there, like a snooker ball, and dropping a ball on it, and it coming directly up. His statement was something along the lines of, for that to happen, the placement of the ball landing on the one below would have to be like within like a molecule's width. Like it's not going to happen ever because of the scale of the precision with which that, so we do it on a computer and it will happen. You do it in the real world, it's just never going to happen. Because what's going on underneath these things, even though this is a deterministic system, what you get is things that look like randomness. And someone mentioned entropy. And of course, this becomes really important as we start to understand heat and where energy goes and how energy is being stored. But the concept of entropy is just disorder in terms of like there's a zero entropy system where things are all going in the same direction. And now we've got a high entropy as we allow that system to sort of collide into each other. And there's principles in thermodynamics that tell us that the entropy is always going to go up. But we can very strongly think about a theory of entropy as being a theory of ignorance. How much ignorance we have about what's going on in this system. So what tends to happen over time is ignorance goes up. And that's like a fundamental law of thermodynamics. It's coming from statistical behavior underlying things, but it's a law of thermodynamics that we observe macroscopically that entropy increases. And we can even have a little histogram of what that entropy looks like. And I've left it running long enough. You'll see that that was the speed initially is giving us a spike near zero, in this histogram. But as I increase the number of histogram that again, so I'm skipping 1,000 seconds of simulation every time I click. You'll see that spike starts disappearing because it's an initial condition. And we end up in what's known as the stationary distribution of this system that is provably Gaussian. So we have to mention Cambridge people. Who worked that out? Important person? Maxwell. Maxwell derived that that's going to be the case. So you can take this deterministic system, and in an ideal gas, that's effectively a model of an ideal gas, you'll end up with gas. So that's what's going on around us at the moment. Everything's bouncing around in a Gaussian way. So there's this really interesting, so the interesting thing is that Laplace has his principle of indifference. He misses the Gaussian distribution. Gauss doesn't have a principle as to why he's using the Gaussian distribution other than the math works. He has no justification other than the math is nice. But then Laplace comes back later and shows central limit theorem. And central limit theorem says is, you know, the sort of underlying thing that causes this type of thing to happen, and means why it's often reasonable, and not always, because you had to have additive systems, et cetera, for central limit theorem to apply, but why often things can converge to a sort of Gaussian. But of course, they aren't always Gaussian. So that's sort of, that's just a plot for one of these histograms I've done with the Gaussian probability density. So we line up a few people that are really responsible for looking at this. It's sort of like you had to have a really big beard in those days, you know, apparently, to work on these things. You know, when I first started talking about this, beards weren't in at all. Only like 5 computer scientists had big beards, but now they're in again. These people would look normal walking around. Of course, they would probably have tattoos and be in a coffee bar. But this is Maxwell, Boltzmann, Gibbs, the 3 probably most important people in this field of what's called statistical mechanics. So looking at the way materials behave as temperature changes, phase shifts, all this sort of thing. And who's super famous? Who do we have who we should be mentioning right now at this moment because of the Nobel Prize in Physics? Giorgio Parisi. Mean field theory is all about statistical mechanics and complex systems and behaviors that emerge from this absolute uncertainty at the lowest level, translating to something certain at the high level. So I'm going to have to speed up now. This is Boltzmann's paper where he shows how this happens for gases. No one believed him at the time. He ended up committing suicide because he was so depressed about the fact that no one took his scientific idea seriously. There was an entire mafia led, I think, mainly by Mark, as in Mark Number, against Boltzmann's ideas. I'm going to skip that other story there and just go to sort of how that resolved. That resolves with this gentleman. You must be able to know who this gentleman is. So Albert Einstein, one of the things he looked at in his Annus Mirabilis is not all the things that we think of him most for. What did he look at? That's what it says at the top, Brownian motion. Right, so one of his papers in that year studied this effect of Brownian motion, because this effect was being observed at a macroscopic scale by Robert Brown in the middle of the 19th century. And he was looking, it's not a particle of pollen, people get confused. He was looking inside a particle of pollen because he was interested in things like sexual reproduction in plants. And he was looking in a void, and he noticed a particle sitting in the liquid in the void was moving in this way. Okay, now, if you want to, this is giving you a totally misleading impression. If you want to get an idea of the scale, I think the largest man-made object on the Earth is some enormous Norwegian oil platform, right? Take one of those, put it into space, and throw a tennis ball at it, and that is the scale that Brownian motion is occurring on, right? It would move only imperceptibly, but of course, if you're looking under a microscope, the imperceptibly small movement would be visible. Yeah, so that's the scale. This is totally misleading in terms of what you see here, but that was this was a mystery, because Brown was able to show this thing isn't alive as far as they can tell, but it's moving. And then, of course, it's Einstein that ends up coming up with stochastic differential equations. He invents stochastic differential equations to model this system and say, well, imagine that this is being hit. If you've done Dirac delta functions in engineering or whatever, you imagine this thing's being hit with a number of Dirac delta functions, which is a sort of white noise process. And that's kind of the math that is going to underpin, I mean, we're not going to go too much into the details of those STEs, the models that we use to deal with this uncertainty. And the person we can really credit for that is the final person I'll mention today, Norbert Vain. So Norbert Vain, he was in Cambridge when he heard about Einstein's paper. He was working with Bertrand Russell, and him and Russell hated each other. because he hated what Russell was saying because his was a theory of knowledge. And Wiener said, you don't need a theory of knowledge, you need a theory of ignorance. But he met Hardy, and Hardy, well, Russell introduced him to Einstein's papers, and he met Hardy, who was also here in Cambridge, and he combined those ideas to come up with the mathematical underpinnings of those stochastic processes that we know them as Wiener processes today. Not only that, he used them, and this is a famous wartime report he wrote, 1942, to try and extrapolate and predict the challenge they were facing was trying to shoot down aircraft. So that's a big extrapolation problem, right? You've got to shoot your gun up where the aircraft's going to be, and the aircraft is doing that. And so Wiener used these processes to predict what the firing pattern should be in order to shoot down aircraft. Those systems were used, they were used in the Second World War, but these are the systems that like were illegal to export to places like Iraq and whatever until relatively recently, because it was that hard a job. And Wiener worked out the maths here. This was a secret report until 1949, but effectively he was doing this extrapolation with this underlying physical model that, that is assuming the pilot's doing Brownian motion. And that's the sort of thing that we're going to end up doing in practice, not for war things. We're not doing any war stuff in what we're doing. We're just going to do it for simulations, climate, whatever you choose, and use these ideas, combine them together. You see, we've got ideas from multiple different fields in order to do these answers. And with that, I should stop there because I've already overrun a little bit, but just check if there's any questions.
Quick question. Do we not implicitly use do we not implicitly decide, even when we regard the model as prediction? I'm just recalling that slide where we have model and data and we're computing for prediction. And you noted that some areas like statistics or machine learning doesn't necessarily focus too much on decision. But for instance, if I classify a photo of a cat as a cat, I've made a decision given my model classified as a cat. So.
Yeah, so that's quite right. So question is like, aren't we deciding when we're classifying that that's a cat? Yeah, so we're conflating a very simple decision. And you can start doing things like, you can do like decision theory on that decision, because what you often are doing is predicting a probability that it's a cat. And then, you know, there's costs associated with that. Thresholds. But we're going to go a bit deeper into that side of things around acquisition functions and how we make decisions. Because say, if it's not, like if you look at something like supply chain, you have to have much more complex model. Other questions? Have anything I missed?
Nope, I don't think so. Yeah.
So yeah. Oh,
How are groups formed for the project?
how are groups? I can't remember how we did last year. We waited a while.
Yeah, we tried to cover that. Because it's quite free, what you can actually do, right? So we tried to first, we did some survey and we checked what people are actually interested in, and we tried to do basically, you think we all deal in uncertainty, so we derive from probability distribution, sample here, and also we'll figure it out.
But it's going to be based partially, as Carl said, on a survey of you and what your interests are. So we're putting you together with people that want to work on similar things. Yeah. Okay, thanks very much. It is nice to be in person, isn't it? How good is that?